So, we started our discussion on cell buckling, and I emphasize the importance of that, and we have started discussion with a considering the axisymmetric buckling of cylindrical cell, right? That's what we started. So, essentially we did not consider any bending, So, if you see the cylindrical cell, we essentially considered the bending, for a strip, we have taken a small strip, right, and that. So, it is one way bending. We did not consider any, circumferential, any bending in that circumferential direction, right, and that, this assumption that essentially the bend, buckling of cylindrical cell, axisymmetric buckling of cylindrical cell can be described reasonably using that, the bending of a single strip, that is a reasonable assumption for this case, okay. And then if you can recall that we have derived the governing equation. See, because of this curvature there is a, and our choice of coordinate system was something like this. So, longitudinal direction was this x, radial direction was this y, right, and z was outward, right, along the thickness, right. And then as you see that, it will have this in plane stresses, right. So, NYY, right, NYY, and then because it is, this angle and this angle will be, this is radius r. So, we are considering component of NYY along radial direction, right, and that basically will add to the effective external, I mean we can consider that to be the transverse load which is contributing in the effective external pressure, okay, analogous to, okay. And then we have written, so essentially when we consider it to be the bending of a strip, then we can, and of course we have taken into account the component of the in plane forces, okay. Then we have seen that we essentially can describe the bending using the bending in the x direction or longitudinal direction, okay. And that is what in the previous class we have derived the governing equation. The governing equation was del 4 w del x 4 minus nxx d2 w dx2 and plus eh by r square w is equal to 0. So, if you see, this is very similar to what? This equation is analogous to buckling of beam founded on elastic foundation, right, or resting on elastic foundation, right. Because for a beam, of course its flexural stiffness was Zi, I mean d. Then this one, Kw, this is the modulus of this subgrade, subgrade reaction K, right. Because if you consider the buckling of a beam, you see that this beam, which is supported on elastic foundation, and then P in both ends, then you are applying this force. Then as you see that the beam column equation is what? Ei d4 w dx4, right, fine. Then whatever is the axial force P d2 w dx2, right, plus additional reaction forces that is going to come is k into w essentially. So, here effectively k into w is coming. So, EH by R square is essentially contributing, that will be analogous to the subgrade reaction, right. So, now we can solve this thing. The solution we can obtain only. So, you must know the limitation of this governing equation, right, and this kind of model. The behavior, the buckling behavior of a cylindrical cell means it is only having only one curvature, its radial direction, right. In other directions, say infinite radius of curvature, right, okay, R, and that's what. And what another thing what I was, so then if it buckles in axisymmetric, so you know, so like this, you see that. So, essentially the buckles are having this pattern is appearing in the along the longitudinal direction, right, in radial, and essentially this simplification we are adapting to describe these things. So, we are essentially taking a, so bending is so dominant along longitudinal directions that we can essentially take a single strip over there, and then we can write down the governing equation for this, and then of course the because of this curvature contribution of n yy will be there, okay, in the along the radial direction. So, that is what we have taken into account while derive this equation, right. So, then we can assume the solution to be of the form earlier we have sin alpha I, and here we are defining alpha L to be pi. So, it is a half wavelength basically, alpha L to be pi, because alpha is the number of half wavelength, right, number of half wavelength, half sine wavelength, sine wavelength. Half sine wavelength means, you know, we are assuming this shape to be sinusoidal. So, how many alpha is there? This one, that one, you see that is alpha, so it is integer. So, then with this kind of assumption, and then you substitute in the equation, and substituting what we are going to get, if we write, you know, this you are going to get as H is the thickness of the cell, right, cell thickness H. We can also write it in terms of T, right, but we are using H just to follow the convention in the book, right. Non-trivial solution sin alpha x cannot be 0. So, this one must be 0, this part, right. So, if you want to make it 0, then from there we are solving, you know, solving for in xx, and it is a critical value. So, in xx will be so that is the critical value that you are going to get, right. And we see that alpha L is equal to pi, because all the half wavelength must be accommodated, right. So, basically alpha is nothing but pi by L, right. So, you substitute for the value here. So, this you will get d alpha square plus E H by R alpha square, right? Now, the way for in plate bending, what we did, we try to minimize nxx with respect to number of half wavelength, right? Alpha. That's what. So, whatever we're doing is following whatever we have done in the plate equation, right? So for minimize is for minimization of nxx, let us put nxx d alpha v0. So essentially what we get here, if you differentiate, for this alpha is this, and then substituting this alpha, substituting alpha with so for that alpha, so we want to see that how many half wavelengths is there, and for which it can be minimum. So nxx, minimum or critical, this value will be if we simplify it, this you will get 2. So that is the expression you are going to get. See, it is not always that. So we get a very simple expression for the nx, what will be the, critical value of this nx, because this was the cell, buckling of cell, under axial compression, that's what we have assumed. So this was essentially value of that, right? Buckling of cell, cylindrical cell under axial. So we obtain a very nice expression. Of course, this expression, although it will never reach, okay, because this is very idealistic, and I will explain to you what really happened there, okay. It's not so simple, cell buckling, okay. So here, of course, for simplification, we have assumed that alpha phi is equal to phi, that means alpha is an integer, but it is not necessarily so. Not that all the time when integer number of wavelength will be accommodated within this length. That is not the case, okay. This expression is very simple. So you may think that, well, if we take a test cylinder and we test it, we will get it, but it's not. So if the length is not compatible, so what we have seen that in plate buckling, because this is analogous to plate, that if the half wavelengths are compatible to the length, that means the half wavelength appears in a integer number, right? Then it attains minimum value. Otherwise, in both sides it increases, and that's what it gives tongue-like structure, right? Which you call it Arnold's tongue, right? Similar kind of things will also happen here. Okay, if this is not compatible, if the length of is not compatible to integer half wavelength, wavelength, that means alpha L is not equal to pi, then it will increase in both sides, okay. So we get in xx d alpha square plus r square d alpha square. So this is alpha depending n pi by L, okay. So this is n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4. And you see that minimum load is that's what you have obtained here. This is nothing but 2 root E H D by pi r square, okay. So when this alpha is an integer, okay, that means the length of the cylinder is good enough to accommodate integer number of half wavelength, then it will attain the it is irrespective of number of wavelength, it can be 1, 2, 3, right. So then if the minimum value is attained, and minimum value is given by this, otherwise it will the load is increasing, okay. And that expressions you have seen, it is nothing but d alpha square plus E square. So this one, for n not if n is not an integer, then it will increase, right. And this is basically, so that's where and for that give increasing number of wavelength, the modal transition occurs. So mode conversion, so for first mode it will go to second mode, that means from single wavelength it will immediately jump into 2 wavelength and then 3 wavelength, something like that. So this is very similar to the behavior what we have observed in plate buckling, right, clear. So this is a very simplified representation of cell buckling, and this is very based on the assumption then the cylindrical cell, it will be subjected to axisymmetric mode of buckling, okay. And we can essentially represent the bending behavior using a single strip, right, and incorporating the curvature, effect of curvature and circumferential direction in the while derive the equations, right. But and then we get a minimum value, but this doesn't really occur, okay. The equation is very similar to the, it's analogous to the buckling, to the equation which governs the buckling of beam on elastic founded on elastic foundation, right, and we obtain a very nice closed form expression. The thing is that cylindrical cell hardly bend in axis, initially it might bend in axisymmetric mode, right, but as soon as buckling triggered, it is not only single axisymmetric mode, but antisymmetric mode will also come, okay. And it's essentially, if you do experiment, it is a combination of symmetric and axisymmetric mode, and for that case it is not possible to have the whatever assumption we made, okay. And also what happens in other than this, that along with this bending in longitudinal direction, this will also be accompanied by bending in the transverse radial direction, right. And unlike plate, there will be even if we consider the first order theory, there will be coupling between bending and membrane term, okay. That's what we are going to do now, and we will follow the quasi shallow cell theory, in which we will assume that the buckling mode consists of wavelength, and each of which can be represented as a shallow cell, okay. That means it's, so we will derive this quasi shallow cell theory, quasi shallow cell cell, and buckling of that, and then we will derive the, from this we will essentially obtain the Donnell equation, okay, Donnell. this is a Donell equation for cell buckling. But please note that even here, whatever we are doing is not what is observed in cell buckling. Cell buckling is way complicated. This is just one step of, in fact, the buckling of cell, if you see it had, it has came on long way. There have been effort, continuous effort by many scientists. Okay, so if you read the book by Bruce and Almorth, and they themselves also contributed, Calladine, Bushnell, and then of course von Karman. Okay, and then there are a number of scientists. Okay, and then there was Donell, including Donell. Okay, so initially with this, whatever we are doing here, we using simple equation, they try to describe it, but it was not matching with what we observed experimentally. But nevertheless, let us see that how this evolution occurs actually, okay, in the theory. So now we will see that how Donell equations is derived. Okay, so quasi-shallow cell theory means like you have a cell, right, and then it has radius of curvature, these are right, and then of course it will buckle, right. So it will have this buckling wavelength, right, and it will have this amplitude, right, these amplitudes, right. So see, this amplitude we may assume that while it is A. So A by R is very, very negligibly small than 1. Then this is called like each buckle, each half wavelength, for the buckle, describing the buckle, is essentially behaving like a shallow cell. Okay, so that's what is. So this is one of the assumptions while deriving the Donell's equation. Okay, and then unlike plate theory in which, see, in plate theory, the bending and in plane forces coupling we observe under moderately large deformation, right. We have seen that at least the linearized theory, in the linearized theory, we assume that the axial forces, the in-plane forces were essentially constant throughout the plate, right. That is what the assumption was, right. And essentially there was no coupling between the in-plane forces and then the bending, out of plane bending, right. There was, unless you consider the moderate deformation which was described with the von Karman-Poppel equations, right. But unlike plate, because of the curvature, in cell, the in-plane forces and then out of plane bending, these two are coupled essentially. Okay. So from the very beginning, we have to consider in-plane forces, equilibrium of the in-plane forces as well. So that's a difference between the plate theory and the cell theory. Okay, for buckling, the bending, in-plane forces and bending coupling doesn't occur, under small deformation or whatever in the pre-buckling regime, right? Or if you want to find out the critical load, whatever. For the plate, the coupling occurs only in the post-critical regime. Unlike that, in cell, the buckling is set in from the very beginning. Okay, so that's what we are going to write. So in plane equilibrium, so Donell's give this equation. So here you please see that secondary membrane forces. What is secondary membrane? Why this secondary? Why not primary? What is primary membrane forces? By now you understand that. Secondary means, see, initially the plate is subjected to some axial force, right? And we assume that to be constant, and we find out critical value of that, right? So that we refer to as primary forces in the pre-critical or even on the verge of buckling, right? Isn't it? But as soon as it buckle and then moderate deformations, take place, right? Then there is a redistribution of that forces, right? And because of that, there is secondary forces that occurs, right? Isn't it? And that's what we call. But here in the Donell equation, in the plate, in the cell, secondary member forces has to be considered. along with the primary forces. You understand that, right? And why that is so? Because of this coupling. Okay? Must be considered, I am writing it, must be considered in a, even in a linear cell theory and unlike plate theory. Okay, this is a big difference. Okay, so in plane equilibrium of the in-plane forces, you may wonder here why we are not considering r, theta and others, right? Because that is more, see, in plate bending theory, right? In plate bending theory, you have considered for cylindrical, coordinate system r, theta and z, right, for the cylinder, and for the spherical r, theta and phi, right? For this was for cylindrical cell, and this is for spherical, right, or dome, spherical, and there was for the conical. What was the coordinate system? R, theta, and then L, slant height, right? And of course, all these things can be combined using generalized curvilinear coordinate, right? Curvilinear coordinate system, right? You have all learned this one in bending theory of plate, the concept of generalized curvilinear coordinate system, covariant base vector, contravariant base vector, right? Gauss-Kodaji relationship, right? Anticlastic curvature, synclastic curvature, all these things you have learned, right? Good. First fundamental form of surface, second fundamental form of surface, all these things you have learned, right? Good. Here we are not going to that much, okay? We are essentially restricting ourselves, and we are considering, even you will see that we there are three very simple problems which for which we derive the linearized equation for cell buckling. Once again for the cylindrical cell, okay, for the spherical, for the cylindrical cell, and we essentially adopt like x to be along the longitudinal axis, y along the radial axis, okay, and z along the thickness axis, okay. So thereby we avoid all these things, okay, whatever. Nevertheless, all these things are extremely important, because please note that all this, everything can be combined into one generalized coordinate system, and it can be specialized to all of these. That is useful when you derive finite element, because although we are deriving all the theory, etc., but in research or nowadays all the investigation essential, except very few who still want to do analytical solutions and things, using perturbation, asymptotic expansion and things. People do finite element, and for in formulating finite element, for that, if you know these things, it will be easier, you can easily follow the paper. Most of the literature is written, okay, using curvilinear coordinate, those conventions, okay. You have to know both the indicial, you must be conversant with the indicial notations, okay, summation convention, and along with that curve, the differential geometry, okay, where you are taught this the curvilinear coordinate system and theory of surfaces and others, okay. Little bit of differential geometry you should know, okay. All of you have learned this metric tensor, right? See, these are all these discussions are also very much essential to your friends, in physics. These people who do large, theoretical physics, large, high energy physics, and that study theory of relativity and others, right? There, the first lesson they learn in, differential geometry, okay, and then the difference is that what we do, our metric tensor is essentially spatial coordinate, right? our space and time is separated, but their time is also, so they define unit tensors, unit metric tensor based on that. So you can see the complexities involved. Okay, so mathematics, theory wise, mathematics wise, both are in the same line. Okay, this we have already derived, so you know this thing. I am just once again reiterating. So this equation must be satisfied the secondary forces, right? This is the equilibrium equation, and in plane and out of plane equilibrium, this I am not deriving, you are going to understand that. We have already derived for plate, right? So you can understand which term is contributing what. Now we are considering only cylindrical. Okay, please note that. For spherical things will be more complicated. This is the so 2, and this is the third equation. Of course, then so you understand that from where this 1 by r is coming, right? This 1 by r is coming from the, see, this is the curvature terms, one second, from the bending, right? And this is radius of curvature. So 1 by r is the radius, one second, curvature, right? So along with the whatever curvature due to deformation, the existing curvature in the geometry is also contributing that. Please try to understand this term, right? Both are curvature term, right? Okay. I am writing the component of the components, all individual component of the theory, and then I will finally write the equation. And that's where essentially what equation? Donnell's equation. Okay, Donnell's. So not force deformation actually, this is just the deformation component, deformation and strain component, okay. So you see that U0 stands for the whatever of the in plane, okay, and B stands for the contribution from the bending, okay. 0 was the for the in plane forces, okay, in plane contribution, from the in plane forces, and B is for the out of plane bending basically, or bending is always out of plane, right. So since, see, buckling, in the pre-buckling regime basically there is no bending, right. So all were in plane forces, that's what and that's basically the ground state, right. So that's what I am defining 0 0 0 0 0, okay. and then once it buckle, then of course that will be accompanied by bending. That's what the component of bending is coming there. Understand that? Then I will write moment curvature relation. You know these things, this we have all derived. Depending on the sign convention, there will be negative signs, right? And cross, these are the bending moment expressed in terms of curvature, and then the torsion moment expressed in terms of cross curvature. Then I will just write the some strain component, strain displacement relations. Okay. So as you see that epsilon y will be del V0 by del y, and then minus W by R. From where W by R is coming? W by R is coming, okay. See, it is radially expanding, right? So 2 pi R, and then the way this term is coming, 2 pi R plus W minus 2 pi R divided by R. That's what V by W by R. W without plane deflection, right? And del V del Y, del V0 del Y is, you have learned from the small deformation theory, right? Epsilon, fine. So this is 0. Okay, so I am removing. So essentially what we are going to do, I will now write down the expression for Nx, Ny and Nxy, okay. So you have obtained the expression for the bending moment, you have obtained the strain and the displacement, expressed strain in terms of displacement component, and we have the equilibrium equation, right. So the thing that is remaining is Nx, Ny and Nxy, okay, in terms of in-plane forces, right. The strain, this we will express in terms of in plane, we will use stress strain relationship to express this in terms of stresses, and then stresses in terms of strain, strain in terms of displacement gradient, okay. And then ultimately we will substitute into this equation, equilibrium. Now middle surface stresses, okay, other than whatever is externally applied, primary Nx0, Ny, Ny0, and there is also the secondary one which is coming due to bending will also be expressed. That is what I am just writing, okay. So Eh by this is the primary one and this is the secondary one, okay. Please note that W will come only due to bending, right. And now I understand why the from the very beginning this coupling will be there. Understand that? I will try to explain using the Ronell equation itself. Okay, wait please. So, now that all components we are having, okay, all of this we will substitute in the equilibrium equation, and then we will just reorient the term, okay. Then we are doing it for the essentially for the cylindrical cell for simplification. There can be very generalized equations, okay, that we could have also learned, but then I wanted to avoid the mathematical complexity, okay. Want to make the discussion simple, but essentially we will try to focus on the physics of the problem, okay, what really happens, okay, with demonstration on cylindrical cell, because cylindrical cell, if we understand, that can be extrapolated for other cell essentially. Whatever is happening due to additional curvature, etc., there might be qualitative difference, quantitative difference, but not qualitative, okay, things. So, then substitute the equation you will get, this is Donnell equation. Donnell equation, this is a 8th order equation, okay. Once again, the way for plate you have derived this, okay, nabla square Wxy is equal to Qx by d, right. Similar equation, the only thing is that d nabla square, so essentially 8th order, okay. W minus nabla square you see, this is the equation ultimately. You see, curvature in the cylindrical cell, this is coming in this term, right. So, this is the Donnell equation for, of course, cylindrical cell. What? So, we will use this equation, we will make use of this equation to study the 3 cases we can study, okay. Although we will not have time to study 3 cases, 3 simple. One is, we will only study the first one, cylindrical cell, subjected to axial compression. Right, cylindrical cell subjected to torsion, it can result into torsional buckling, right, and cylindrical cell subjected to in plane the external pressure, subjected to external pressure, external pressure, and then when it is subjected to external pressure, there will be hoop stresses develop, right, circumferential hoop stresses, and then because of that, then it will also buckle, right. So, these 3 simple analytical solution can be obtained, although all this analytical solution essentially the first one is meaningless, because what happens, what is predicted by this equation for the second and 2 is reasonably, to a certain extent it is good, because those are not imperfection sensitive. Once again, imperfection sensitivity will come into picture when it is subjected to not the small cell buckling problem, or under all the loading mode are imperfection sensitive. Please note that a cylindrical cell subjected to axial compression is very notoriously imperfection sensitive. So, that is what it also mobilizes a huge post-critical nonlinearity and even pre-buckling nonlinearity, and that's what it basically collapses the whatever the little theory that we're trying to erect. Okay, but for the other it might be little closer. Okay, fine. So the first one I am going to show that what essentially you get, and then how that the experimental result or actual behavior of the cell doesn't even comply to that. Okay. We will consider cylindrical cell subjected to axial compression. Once again, you please note that cylindrical cell subjected to axial compression, we have studied using in the first example using the axisymmetric, assuming that this is there must be axisymmetric buckling mode, and essentially the bending can be represented by studying the bending of a strip, and essentially we will have a one-way bending, and we established this analogy with the beam on elastic foundation, and we have seen. So this is another way. You see that increasingly we are imposing more and more complexity. Okay. So this, when we are going to put there, how the equations will look like. We are considering a cylinder, right, cylindrical cell. Axial compression, huh? Huh? So sigma x into h is basically the, assuming this is sigma x and h is the thickness, so that is nothing but nx. Okay. So the coordinate axis, this is x, this is y, and this one is z. Huh? We assume the solution, and we assume the boundary conditions, right? Assume simply supported, so W is equal to 0 at x is equal to 0 and x is equal to L, and then we also assume that because of it is, if we assume this simply supported out of plane, it's a restraint. So see, because it is axisymmetric, and then if we assume W is equal to 0 and in the y direction, the bending expression, if you see that bending moment need to be 0, right? So from there, if we simplify, then other derivative will drop, only this derivative will remain. So that must be 0. Okay. So this is essentially the boundary conditions. Now we can assume the solution in terms of x and y, right? X and y. We assume the solution by satisfying the boundary condition. So when we satisfy the boundary condition, we will W0 sin m pi x upon L sin beta pi y upon L. Okay, where beta is equal to n L by pi r. So essentially what we try to do is we first assume, this one is coming from somewhere, this is coming, we assume this is W0 sine m pi x upon L, right? And then we assume sine L is basically the pi into R, right? 2 pi R rather, pi into R, and then it is n pi y. N pi y by pi R. Pi R is the length, right? So then we assume this to be beta, and then we substitute something like this, okay? Essentially consisting of half sine wavelength, okay? The difference with the first one and here is that here we consider both way bending, bending along x as well as bending along y, and both the bending we assume that we we can approximate using sinusoidal function, okay? So essentially we assume what, that we are restricting a priori that it will buckle in a square pattern. Why? Because you see that this will so along x direction it is all this sinusoidal kind of pattern, along r direction also it is this kind of pattern. So you see that how this sinusoidal kind of this curve is coming, okay? So a priori fix it that it is buckling with this kind of assumption, we buckling in square pattern. So this is a basically there is a problem, when we are saying that while it is buckling in the square pattern, that by using sinusoidal approximation, this is a huge simplification of the problem. If you do experiment and if you see what happens, it doesn't buckle in the square pattern at all. Now, if you take a cylindrical, unfortunately we don't have setup to do this experiment. This is a very interesting experiment and it's a very interesting physics comparing the experiment that we are doing now, okay? When it buckles, you will see that it develops pattern which looks like diamond. So it doesn't buckle under square pattern, it buckles under diamond pattern. And how does diamond pattern look like? The diamond pattern is something like this, right? So essentially what happens is that if there is this kind of cell, cylindrical cell, and what will happen that a portion of this will come out, so and then so it consists of two ridges and two furrows. See what is ridges and what is furrow. See, this is coming upward, right? This is coming outward. The next way it is coming inward. So that's what this kind of diamond pattern is, okay? This is a diamond pattern. And then you see, so diamond pattern, inclined pattern, and what happened that one will come out, one will go in, this one, okay? So it will be something like this, okay? So it consists of a number of ridges and number of furrows, okay? Consists of ridges and furrows. So white buckle under square pattern, that can be explained, I will explain later. What happened that when it try to buckle, essentially the buckling need to be, the cylinder need to experience the membrane stretching, because as you are pushing me, I am going to stretch it like this, right? So the membrane stretching is happening, and how membrane stretching is happening? So out of plane deflection, and because of out of plane deflection, there is a in plane force, in plane strain, bond carbon strain, right? So that tries to happen initially, that's what load increases, but then suddenly it goes to a configuration with a diamond pattern. And all this diamond pattern, if you see, if you sum up this, this this whatever is coming up, these ridges, you will see that the length of these ridges will essentially be same as the circumference of the cylinder. So, what does it means? That means essentially it's an inextensible mapping of the surface. And when there is inextensible mapping, that means what you understand, that essentially there is no, maybe initially there may be little membrane stretch, but later stage essentially there is no contribution of strain energy by membrane stretching. Entire contribution of strain energy is consumed by bending. So, it is a pure bending, in a that is corroborated by inextensible mapping of the surface. And this kind of pattern, this you have to be careful to do this experiment. It cannot be. What you have to do, you have to take you will search in YouTube or search in book, you will see this picture, So, you have to take this cylinder and you have to put a mandrel inside it, so that it radially, so the cylinder basically rests on a mandrel. So, that means it does not go inward. Okay, you see that in order to develop this pattern. So, a mandrel, it will be mounted on a mandrel, so radially supported by a mandrel, and then gradually you apply the load using a, of course, displacement control or strain control experiment. Okay, and gradually this pattern will develop. If you do not do, then you will not see this beautiful pattern from the end and it is propagating over the length. Okay. In fact, we wrote a paper and then we were all ignorant, me and my students were. So, wrongly I was associating some pattern what we saw in the simulation, finite element simulation, to Yoshimura pattern. This pattern is called Yoshimura pattern, okay, named after some Japanese scientist, Yoshimura. This is a huge nonlinear phenomena, okay, I will explain it later. But so then the reviewer rectified us that no, you are wrong actually. So then of course we studied, and that's what what I suggest, that you read more and more you will read, more and more you will learn that how little do you know. Okay, that was told by one of my Professor IIT Bombay. You see. Anyway, so whatever we obtain from here, that I will show it to you, and then I will introduce to parameters which are extremely important. But then please note that it does not corroborate with that. In fact, later Donnell himself, he tried to solve his equation using this, assuming this diamond pattern instead of sinusoidal pattern. But then also he failed. You know why he failed? He failed because he did not consider nonlinearity, neither the p-Wakeling nonlinearity nor the post-critical nonlinearity. Unless and until you consider those nonlinearity, these modal interactions will never occur, and the interactions of these imperfections to the erosion of the membrane strain energy will not be captured. And if you do not capture the nonlinearity, you will not be able to capture the actual behavior that is observed experimentally. So, there is a huge puzzle lasted more than several decades, and ultimately it is von Karman who solved it using asymptotic technique and give a meaningful solution to this problem. Now it is all well understood. So, if you take and substitute in the equation, then substitute in the equation, then what you will get is So you understand why these things are coming, because it's all these numbers. I can just show it to you. Okay. So if you assume like this, then 8 is something number square, number square, number square, number square, right? So then you differentiate all the so this is nothing but 1 lambda square is, if you operate 1 lambda square, then you will see that it is nothing but Laplacian operator, right? So del 2 del y2. So if you differentiate then on this, then you will get essentially minus m pi by L square minus beta y by L square, and you will get minus y square by L square m square plus beta square. Okay. So 1 is this one. So if you see so there is 4 times this operation is going on, and essentially it will be raised to 4th power. Understand that, right? Okay. So then from there, if you simplify, you will see that this will obtain an equation. I will simplify it with some variable m square plus beta square to the power 4 plus 12 m kx is equal to pi square d. Kx is essentially, you see that it's a stress coefficient, right? And z is an important parameter. Z is a shape parameter. As you can see, it's essentially a shape parameter for the cell. Shape parameter. Why? Because it's a function. Of course, it's one of the function of the Poisson's ratio, because of it's a two-way bending, so their coupling will be there. So, but essentially it involves the length, radius of curvature and thickness, right? So it's a function of, see, L by R is what? It's a slenderness ratio, right? L by H is like, so essentially it is a geometric parameter that will basically control the buckling. Understand the critical role, right? So that's what it's a shape parameter, and this parameter is called Bardorf parameter. Bardorf, D-O-R-F. This is called Bardorf parameter. Name of the scientist, okay, who have investigated this. Now once again, so Z factor, Z factor essentially helps in distinguishing between short and long cell, long cell, and thick thin cell and thick thin cell. See why? Because L by R, you will distinguish long and short cell. So what happens if the cell is too long? What happens? Its cell action will not be there. It will essentially buckle like a column under axial force, right? So it will differentiate the buckling of short and long cell. And then when we take the L by H is thickness. So it's a thin cell or thick cell. You understand that differentiation. Anyway, so that's what it's a Bardorf parameter. It's an important parameter. And then now, what we will do, you can clearly see that's a function. There are, unlike the previous one where we considered one-way bending, it was only single wavelength. single wave number, right? M and beta. Earlier only was single wave number, but now it's a two-way bending. So two-way bending, so wave number, and this M and beta. So when you are taking square root, that's the combined wave number. So essentially, this is a wave number parameter, right? Now the way you have seen that with changing wave number, there is mode conversion that may occur, right? So we have to minimize this with respect to the wave number. So we can take this to be a combined wave number parameter and differentiate this for minimizing the Kx. Kx essentially is related to the critical stress, right? For that, because it contains the what? Axial force parameter sigma x and sigma x here. Critical value of that we can find out. So if we do that, del Kx by del m square plus beta square and then you will see from there, then you will get a condition for minimization. So condition is, if you simplify this m square or beta square by m square is 12 z square by pi to the power 4. This is the condition for minimization for Kx minimization. And when you are minimizing Kx means also sigma xx minimization. Okay. So this is the condition. So what we see that there must be a relationship that must be established between the effective wave number and then the wave numbers associated with the mode shape of buckling and then the shape parameter of the cell. Right? So from here on some simplification, we will get sigma CR as 1 divided by root 3 1 minus mu square and EH by R. See, I mean this is a little comparable to our previous solution, right? When we assume that the one-way bending and then axisymmetric, right? So that EH by R term was also there, but what was not there is basically this coupling term, because including Poisson's ratio, right? This term was not there. Okay? So this is valid for Y, valid for Z, Beddow parameter greater than 2.85, because Beddow parameter has to be positive. Okay, that I will show it why. This is important. Okay, so then I will stop here today. Next we will see.